Okay, so hi, I'm Derek. We talked about my work this summer on creating synthetic dimensions using multimode waveguides. So before I get to all of that, I need to talk about photonic devices, which are exciting technological advancement to electronics that harness the power of light to transmit and manipulate signal uh, through waveguides. And they're more versatile and more efficient than their classical electronic counterparts. And traditionally, we only use a single mode TE0 within our waveguides. If we draw an analogy to the quantum potential well, higher modes require more and more energy. And so typically, we can only really support the energy required for the ground state. But however, by increasing the width of our waveguide, we can actually decrease the energy required, make it feasible to actually have more modes within our waveguide. So here I have the waveguide I've worked with in simulations that supports modes from TE0 through TE3 with their respective refractive indices calculated by the simulation below. Um, and because my waveguide can support these higher modes reasonably, we call it a multi-mode waveguide. And note that these modes are the eigenmodes of our system corresponding to electric field. Okay, but we have these modes, and by themselves, they're not really that interesting. The interesting things happen when we couple them together. Uh, Basically, this means that there's energy transfer between these modes, or what we call a mode conversion. Note that this doesn't mean that the modes themselves change, just that the state of our light changes. And we can actually couple even more modes together in a kind of a network like this. But why do we care about being able to couple multiple modes together? It's because we can create a synthetic dimension, which is a system's internal degree of freedom that kind of mimics its three spatial dimensions. For our case of light, the modality here, by having this mode conversions, the modality becomes a synthetic dimension. Now, synthetic dimensions are cool because they have applications in being able to create topological photonic lattices, which enable the study of robust and topological photonics, meaning that in these waveguides, we can prevent backscattering due to defects in the waveguide. Now, topological photonic lattices already exist in real life, but they require the coupling of hundreds or even thousands of waveguides. My project is novel because I can, by using all these mode conversions within a singular waveguide, we can significantly downsize the structure sizes for topological photonic lattices, making it much more efficient and much more commercially makeable. But how do we actually create such a waveguide to hold these mode conversions to make a synthetic dimension? So in our case, you can't really see it too well in here because of the lighting, but I use a perturbed waveguide here. Um, Using perturbation theory, which I won't get too deeply into, some perturbations can actually convert the light from one mode to another. We specifically look at sinusoidal perturbations for two reasons. One, they have been mathematically modeled and analytically solved to actually have mode conversions, at least in the 2D simulations. And they're also really easy to model because they're so simplistic. Now, to actually obtain the wanted mode conversions, there are four relevant perturbation parameters. One is the period of a perturbation, which is the expected period for a certain conversion is modeled by this equation up here. The number of periods, which affects the length of a perturbation, and its effect on the mode conversion rate is modeled up here. The amplitude of a perturbation, larger amplitudes mean quicker conversions, but too large of an amplitude also runs the risk of backscattering and unwanted mode conversions. The symmetry of a perturbation, which I will have to talk about a little bit about parity to talk about. Odd parity corresponds to odd number TE modes, like TE3. Even parity corresponds to even numbered TE modes, such as TE2. So same parity conversions, such as TE0, TE2, have symmetric perturbations. Cross parity conversions, such as TE0, TE1, have anti-symmetric perturbations. Okay, but As I previously mentioned, these conversions have already been shown and modeled in 2D. A grad student in the group, Nate, has actually run simulations on these mode conversions and shown that they actually work. However, when we extend our 2D model into the 3D regime, the height, even if it's a constant height, adds an extra layer of complexity to the system such that there doesn't exist any analytical solutions to this perturbed system. Thus, to determine how we need to adjust our 2D model to work in 3D, we need to run some simulations. So I use Lumerical here to model the simulation, to simulate the evolution of our E field over time. And here's the kind of the basic framework I use to do such a simulation. We start off with our perturbed waveguide and our unperturbed sections. Input port, which sends in light through the waveguide. An output port, which actually takes in the output light and breaks it down into its modal components. And I have a little tapering here to smooth out some sharp edges that might exist due to non-integer numbers of periods, which might cause backscattering. Okay, so after doing some sweeps over perturbation period, amplitude, and length to try to maximize the mode conversion rates for each of these conversions, we were actually able to see the conversions, and you can visualize it here through monitors of the electric field intensity. So here we have TE0 to TE2 and TE1 to TE3, as noted by the number of peaks in the electric field. And also, we also saw this for TE0 to TE1 and TE2 to TE3. These are not as good as conversions, as you can tell from how not as nice they are compared to these. One thing I like to point out, though, is that in TE0 to TE1, you can actually see a little bit of the perturbation of the waveguide due to the bumps in the edges of this section right here. Okay, so since our goal is to have synthetic dimensions be generated by multiple mode couplings within a singular waveguide, one method for doing so is to have all mode conversions actually happen simultaneously within a singular waveguide, therefore coupling all the related modes. For a system I'm interested in, such a mode coupling network will look like this, where the arrows here represent mode conversions, which are technically reversible given an infinite waveguide. But one thing we have to account for is that these have to have all equal rates of mode conversion, simply because if they were unequal, we wouldn't actually be generating a degree of freedom based on modality. Here, I chose all these rates to be around 20%, because it's high enough to actually see conversion, but low enough to not need actually optimize perturbation parameters. Okay, but in 2D, we did this through superpositioning all of the modes together into a singular, superpositioning all perturbations in each other to get a singular perturbation of a singular waveguide. But again, due to the complexities of a 3D system, this is not actually guaranteed to work again, especially since we have same parity mode conversions, which contribute to a nonlinear model due to the varying waveguide length width. So I had to run some simulations by superpositioning all my earlier perturbations to actually see if it works. And so by simulating it, we can actually see the electric field changing over mode changing over the length of the waveguide. And this is not so nice to actually see what's happening. So I have this little model here with the mode decomposition throughout the waveguide. And as you can see, we start off with TE0. It eventually gets decomposed into TE1, which then gets decomposed into TE3. And then, but also at the same time, we have TE0 being converted into TE2. And so therefore, we actually see all the modes existing within this waveguide. And because of that, by having all these modes together, we can see that we successfully computationally shown a 3D multimode waveguide that supports multiple simultaneous mode conversions throughout our superpositioning. And therefore, we have actually formed a synthetic dimension within these simulations. And so there are a lot of future steps with this project, but what I want to point out specifically is being able to test these actual structures experimentally on devices, because I could have briefly mentioned my other project this summer, which is assembling this setup to actually measure the transmission of light throughout the devices. I'd like to quickly thank both my mentors and other grad students in my group for helping with both my projects this summer. And special thanks to Niloy who recently graduated from Carlos's group for helping me out with setting up a lot of the early simulation stuff. And thank you for Daniel Serrano for helping with so many logistical issues with the Trend program. Yeah, I went through everything quickly, so if you come to the poster session if you have any questions. But thank you.